This is question 5 of the 2016 Scholarship Physics exam. So it is question 5. Right, we have a diagram that shows two masses M1, M2, which is this one here and this one here, on the XY plane or on the Y plane. Initially at rest, connected by a rigid massless rod of length k. Initially, M1 is located at the origin, coordinates 0, 0, and M2 is located at coordinates 0k. So it's up there. Obviously, two additional masses, M3 and M4, travel towards the rods with speeds v and 2v respectively. It's got them up there. Mass M3 strikes M1 at the same time as M4 strikes M2. Both stick to the representative target, so it's a fully inelastic collision. M1, M3, and M4 all have the same mass as M, so I mean I could just chuck in M, and M, and M2 has 2M, just for tracking. So right, show that the XY coordinate of the center of mass of the system immediately after the collision is 0 and then 3/5 k. Right, so the center of mass of a system is you sum up the moments and you divide by the sum of the masses. A moment is just you choose an origin. So at this point, it's from the center of the coordinate system, which is here. So here is our origin, and the moments are measured from there. So we'll just do the XCOM. I mean, I can look at this and say there is, like when these are stuck on, so we've got this one here stuck on, this one here is stuck on. There's nothing either side of the X, like what do you call it? Either side, inside the X, what do you call it? Coordinate system. The whole lot is at the origin, but I'll just show that mathematically. So we've got XCOM is equal to the sum of the moments, which is, let's do xn. This is terrible mathematical notation, but I'm not a math teacher. So sum of the masses, so mass n, and n just means you can go 1, 2, 3, 4, so on and so forth. So we're going to have, the first one is M3, M1, and they're just MM, so it's going to be 2M. 2M times the distance to the origin, which is 0, plus this is 2m plus another m because I've joined, so it's 3m. 3m times 0. I mean, you can see where this is going. Divided by 5m, totally equals 0. Huzzah! XCOM, center of mass. Oh, damn it, not XCOM, YCOM. The center of mass in the Y coordinate system is equal to the sum of the Y, well, like it's the same thing in the Y direction. So we'll start off with the easy one, 2m, because these are just worth m, so 2m, 2m times 0, because they're right at the bottom, they're at the origin, it's pretty easy, plus, how many we got? 3m, and the k away from the origin. So from here to here, where these two, or these like M2 and M4 are joined, it's a k distance. So the distance is k away. So our moment is 3mk divided by the sum of the masses. So we got 1, 2, 3, 4, 5. 5m. And that is equal to 3mk over 5m, which is equal to 3 over 5k. Thus, we have center of mass xy is equal to 0, 3 over 5k. Huzzah! We showed what it asked us for. Right, show that after the collision, the rotational inertia of the system about an axis perpendicular to the xy plane passing through the center of mass is given by that. So perpendicular to the xy plane, that literally means pointing straight up, which means it's rotating around like that. Cool. Right, now we need to, so it's a point, these are all point masses, so I'm going to write point mass The formula for rotational inertia is just mr squared. Because all the mass is at the very end, so it's just mr squared. And because there are, okay, right, we've found the center of mass. I'm going to just chuck, the center of mass is 3/5 away up the pole. So here is the center of mass. Right, so it's rotating around its center of mass, because that's what things do. So now we have to sum up the moments, and rotational inertia, they're all scalars. Yeah, rotational inertia is it a scalar? Pass. I have to think about that for a second. But they sum up. Pretty sure it's a scalar. Right, so that is going to be equal to the sum of the rotational inertias. So sum of the inertias is equal to, what do we do first? We're going to go do the bottom rotational inertia first. So it's going to be m plus n is 2m. And how far away from the center of mass is it? It is 3/5 of the way there. So here's the center of mass, it's 3/5 k down to there, so it's going to be 3/5k squared, and then it's going to be plus, again, we've got 2m plus 1m is 3m. Oh, you can't even see that, whoops. 2m plus 1m is 3m. So we're going to have 3m, and it is, well, if this is 3/5 of the way there, it's 2/5 to here, so it's 2/5 k. So we have bracket 2/5k squared, and that is going to be equal to, I'll chuck that down here. What have we got? 3 squared is 9 times 2 is 18. 18 over 5 squared is 25. mk squared plus 4 times 12, 4 times 3 is 12 over 25 again, mk squared, and that is equal to 18 plus 12 is 30. 30 over 25, mk squared. You can see we're almost there, and that is, simplify that down, 6/5 mk squared. Huzzah! Right, next question. Right, calculate the angular velocity of the system after the collision about the axis defined in part B. Right, so here we're going to use conservation of angular momentum. So we're going to say that the initial angular momentum is equal to the final angular momentum, LF. And you can write it in terms of the formula. So we can figure out the initial angular momentum because we know the velocity and the mass and the velocity. Like, these things are the only things that have angular momentum about this point here. We'll get to that soon. These things here, these masses, M2 and M1, aren't moving, so they have no angular momentum whatsoever. The final angular momentum is going to be these combined with this, and it's going to be sort of spinning like that. Like, it's going to spin like that. And because there's no velocities, no linear velocities in the y direction, that means at the very, the final, after all is said and done, when these are joined, the center of mass will have no velocities in the y direction. So it's just going to rotate around, and the center of mass is just going to track like this. Cool. Rightio. Let's get back to here. So I know what the initial angular momentum is going to be. The final angular momentum is going to be equal to the final rotational inertia, which we calculated just over the page, times the final angular velocity, which is what we're trying to find out, the angular velocity after the collision. Cool, so the initial angular momentum, Li, is going to be equal to the sum of the angular momentums of those little balls. And that is going to be equal to, so I don't know, sum of Li, which is going to be equal to, we'll do the first one. So when it collides, when this one here collides with M2, it came in with 2v times n, m, and the radius is 2/5 k. Because, and these are point sources again, I better quickly chuck the formula for angular momentum. I'll just chuck it up top. Angular momentum for a point source is just mvr. So we're going to have, was it 2m or 2v? Regular m? Yeah, regular m. regular M 2V, and the radius is 2/5 K, 2/5, 2/5K. And now the other angular momentum that's coming in, or it's linear turning angular, so it's linear component, so we're going to have just M, and it is 3/5 K from the center of our rotation. So 3/5 K, so it's just going to be regular M, regular V, 3/5 K, and that is going to be equal to 4/5 plus 3 is 7. 7/5 MVK. Cool. And now we know that the I final is just the rotational inertia of the system, which is just 6/5 MK squared. 6/5 MK squared. And we can just quickly work out omega final, the final angular velocity. So angular velocity final is equal to essentially the angular momentum initial, and we're assuming no external torques because that's the caveat to angular momentum, divided by I don't know, it's just the inertial the rotational inertia final. So that is going to be equal to 7/5 MVK divided by 6/5 MK squared. And just a little side note, if you have, I'll chuck it down here maybe, I'll do it here actually. 7/5 divided by 6/5 is the same as writing 7/5 times 5/6, and you can see that equals 7/6. So the masses cancel, one of the k's cancels out, so we end up with 7/6 times v, and then k is underneath. Cool. And I'll just chuck it down the bottom, and we don't have any numbers to put in, so the angular velocity final is equal to 7v/6k. Right, that caveat I was going to get back to about angular momentum. You can choose any origin about which your angular momentum can be calculated. So unlike linear momentum is linear momentum. It's independent of the origin. Whereas if I chose the origin of rotation, and I found the angular momentum about the origin of rotation, if I chose the origin, as in this point here, that would mean that this this mass would not contribute to the angular momentum, but this mass would. So then the angular momentum I'd have would be 2v times m times k, which would just be, 2m times v times k, which is not, 2m times v times k, which is not the same as this. So now you might have realized that angular momentum isn't really a conserved quantity. It depends on the coordinate system that you use. There was a question, I think, on the 2018 exam where you had two round discs hitting each other, and it was assumed that they'd both rotate off, and they'd both rotate in opposite directions as conservation of angular momentum. But that's not true, because you could choose an angular momentum, you could choose the origin over here somewhere, and then they'd both be somewhat moving around their origin. So yeah, it's a lot more complicated than it's led to believe. So yeah, I don't know, like that. I found that out when I went to attended a guest lecture, and yeah, it blew my mind. I never bothered to think about it. Right, enough rambling. Right, next question. We have m equals, so the mass is 2 kgs, velocity is 2 meters per second, k is 1 meter, is just 1 meter. Calculate x-y coordinates of the combined mass m2, m4 at the time 0.5 seconds after the collision. Right, so I need to, I say right a lot, don't I? It's a weird thing. It's out in the video, but never really in real life. This is going to translate over here somewhere, and it's going to rotate a little bit, half a second, maybe it's probably, I don't know, something like that, and then here's our center of mass. So this new, and what are we trying to find? Trying to find M2, M4, which is the top one. So we're trying to find this one here, which means we need to find this angle here that it's rotated by, and then we need to add this distance that it's gone across. So this distance, I don't know what that is. It'll be the center of mass velocity times time, and it wouldn't have gone up or down, but we'll still need to add 3/5 k to this value here, which is the y value. And this is going to be the x value because I'm just doing xy coordinates. And this is the negative side of the x spectrum, of the x coordinate system, and we're up into the positive side of the y coordinate system. Right, we need to find the angle that I just drew. So I might actually, I need to find the angular velocity to begin with. So our angular velocity is just equal to 7v over 6k, and that is just equal to 2.33 recurring radians per second -1, because I just plug the numbers in. V's 2 and K's 1. Now we need to find our angular distance that we've sort of rotated by, and that is going to be equal to the angular velocity times time, which is going to be equal to, if you put those numbers in, we get 1.6666 radians. 1.166 radians. I have it written down. I don't try and solve these on the fly, otherwise it takes too long. And it is going to be rotating, anti-clockwise. So it's going to be hit there and there. So it's going to be rotating anti-clockwise. Right, I'm going to quickly write that down. So anti, and just because probably people want to know, or maybe if you want to know, I'm going to turn this into degrees. So we are going to get, we're going to times that number by 360, and there is 2 pi in a full circle, 2 pi radians, times by theta, and that is going to give us 66.84 degrees. Right, I'm going to draw a quick wee sketch up. Here's our center of mass of the system. Where's my ruler? Here is that rod. This is what we're looking for, this one here up top. So we need to find the x and y. So this is the y component, this is the x component. This component from here to here is just 2/5 k. We'll call that h. So h is hypotenuse, is equal to 2 over 5k, because again it's just 2/5 from here to here. And now I know this angle here because that's theta, that's the angle that it rotated by, and it's because it's the angular velocity of the rotating system. And now I'm going to figure out what the y and x components are. So the x component is equal to, what is this? This is the opposite. I'll be using sines. So sine theta equals opposite over hypotenuse. I have the hypotenuse, so I'll move the hypotenuse up. So I'm going to have h sine theta. This is hypotenuse, and that is going to be equal to 2/5. K is 1 times sine 66, and that equals 0.367, but it's negative, so it's to the left. So I'm going to make that a negative now, because this is coordinate systems I'm dealing with, so I have to be very careful. This is where you draw pictures and try and visualize it as you go. The y coordinate is by default, it's just going to be h cos theta. I mean, if you've probably done it, I mean, if you're doing scholarship videos, you probably know by now, but it's, yeah, this is, the y is the adjacent. You move the h, it'll be cos theta equals the adjacent over hypotenuse. There you go. And again, that is 0.157, and it's upwards, so it's going to remain positive. Now we need to figure out that origin shifts, because it would have started over here and it would have tracked in the negative x direction over to here somewhere. So because there was no y momentum to begin with, we can expect that we know that the center of mass will have no y velocity. So when we're moving up and down, because there's no y momentum to begin with, there's no y velocity. Like the center of mass will now have no y velocity in the y direction. Right, so I'm going to go origin shift. and I need to, so Vy is equal to 0, but Vx of xcom, so the velocity of the center of mass in the x direction, is going to be the sum of the momentums in the x direction. So I have, what do I have? I have negative 2 Vm, because this is moving backwards, so negative 2 Vm, negative 2 Vm plus, because you always just do plus, is it plus, and this is positive mv to the right, mv, and that is equal to, oh whoops, no, it's not equal to, and then it's divided by the sum of all the masses. So it's going to be divided by 5m, because this is, you add the moments. Oh, no, I skipped the other ones. I mean, I should actually talk about them. This has no x moment, it has no velocity, and this has no velocity. So I would have ordinarily put them into this equation, but just to save space, I didn't, because it'd just be that, it would be no velocity times, what are they? M2 and M1. M2 and M1 don't have any velocity, so I just left them out of the equation. And then we're dividing by the sum of all the masses, which is 5, and that is going to be equal to, what is it equal to? Minus V over 5. And the m's cancel out. Because minus 2 plus 1 gives you minus, it just gives you minus Vm, minus Vm over 5. The m's cancel out and you get minus V over 5. And so we know minus is to the left. So now we need to figure out the new x position. So the x center of mass, I'll just call it nu. I mean, this notation is terrible, but whatever. And that is going to be equal to the velocity of the center of mass, v x times time. And that is going to be equal to, what's the velocity? 2 over 5, which is negative 2 over 5 times a half, which is just 0.5. And that is equal to negative 0.2. Right, now, x, well, it's not really x center, it's the coordinate for what? What am I looking for? The coordinate for M2, M4. So, how do I want to write this? M2, M4, the coordinates. So, and the x coordinate is going to be equal to minus 0.367, and it's just the sum of the how far to the left you went. So it's going to be minus 0.2, and M2, M4 in the y direction is going to be equal to 0.157, and we've gone up. How much have we gone up? Plus this distance here, which is just, because the center of mass hasn't moved, track it back, the center of mass hasn't gone up or down, so that's just 3 over 5k. What the heck was k again? 1. So plus 3/5, which is the same as 6/10. So this is plus 0.6. 0.6. And I should get, how am I going to write it up? X, y is equal to negative 0.5, because 2 plus 3 is 5, 6, 7, comma, 0.757. There we go. And I might just chuck in M1, comma, M4. Right, it's terrible notation, but that's how you solve that question. Right, that's it.